mathematician self-adjoint operator. So it's an operator acting on that Hilbert space. And if you want to measure something, then you have to apply the observable to the wave function and then form the scalar product with the wave function, and you get an expectation value. So this already is pretty involving, but anyway, so it's more than a crash course. So, but the important thing is, how does the dynamics of a quantum mechanical system evolve? It's given by a certain observable, which is called the the Hamiltonian, H hat. And and there we have the famous Schrödinger equation, which tells if you have a quantum mechanical system in a state psi, this state evolves over time via this differential equation called the Schrödinger equation, and invented originally by Schrödinger. Yeah. So how does that have anything to do with energy? So the eigenstates of the Hamiltonian are real, and they give you the potential energies the system can be and you can derive, I mean, if you have here the eigenvalues of the Hamiltonian, H hat psi is E psi, then the system can be in all of these E's, which you can have as eigenvalues of the Hamiltonian. One should be a bit careful because this is only part of the story. It's actually thinking in finite dimensional terms, but the Hilbert space is infinite dimensional. But I will swipe all of the mathematical subtleties here under the rug. So for those who are interested, I have some notes on my webpage. So just ask me and I can send you the precise link about spectral theory of operators. So, and there is always, I mean, the Hamiltonian is assumed to be bounded below. Yeah, so that's by physical reasons, and there's always the lowest eigenvalue, and that corresponds to the ground state. So, and now let's come to a molecule, and classically the energy of a molecule is the energy, the kinetic energy of the nuclei plus the electrons plus the potential energy, which I wrote here by W. And let me just give you the formulas here without going into details. You've all seen this in some, I guess, fundamental basic chemistry or physics class. And so the W here is the electromagnetic potential, and here are the two kinetic energies of the nuclei and the electron. Okay, now in quantum mechanics, you replace the big PIs and the small PIs by these differential operators corresponding to the quantum versions, and then you get the quantum Hamiltonian just by replacing the big PI by this IH bar d by dxi and the little PI by IH bar d by dxi, and insert it in this one here. Anyway, okay, so, and then the idea is to solve this eigenvalue problem for this Hamiltonian H mol. So this is a problem which is mathematically and also numerically essentially not solvable. It's huge, and it's even just finding the lowest eigenvalue, it's way too difficult. So, and now two famous physicists, chemists, mathematicians, Max Born and Oppenheimer in 1927 had the right idea what to do. And the idea they had is separate the electronic motion from the nuclear motion. The idea is that the nuclei move very slowly and the electrons very fast. The nuclei have big mass, the electrons have very small mass. And so the idea is to separate this and then approximate the real the wave function psi x little x by a product of an electronic wave function depending on the position of the nuclei in capital X and of the electrons little x, and then times the wave function of the nuclei. And this is the separated stuff, and which we are not so much interested in. Okay, and expand then everything, the spectral theory in this kappa, which is the quotient by the mass of the electrons, is little m, via the sum of the masses of the nuclei, which is much, much more. So this is a very small parameter. So, and then via this separation, you can reduce your Hamiltonian to an electronic Hamiltonian, just taking the kinetic energy of the electrons plus the potential energy did not change. So, and now, yeah, and it depends on a parameter, namely the big X, which is the position of the nuclei. And then look again, let me just see what, again at the Schrödinger equation. Yeah, here, this one, but just replace it by this new one. And then you get solutions which depend on on the parameter big X. Okay? So for all x and Rn, there's a simple lowest eigenvalue of the electronic Hamiltonian for nuclear position X. It solves this Schrödinger equation just for the electrons. And the family of all those x, E of x, where E of x is the lowest eigenvalue, that forms a surface of R3n plus 1. And that is the so-called potential energy surface for our energy landscape. Yeah? So essentially, this means that the gadget we are looking for and want to study by a topological and geometric and potentially also additional means, that's exactly this guy here. It's still highly complicated, and it's still an idealization, yeah, because this potential energy as defined crucially relies on the Born-Oppenheimer assumptions. I cannot go in all details what that means, but I will give a couple of hints and yeah. So there's another assumption, and that's actually extremely important, and that the spectrum is gapped. That means there's a delta, which is positive, which separates the E of x, that's the lowest eigenstate of here this electronic Hamiltonian from the second one. Yeah, so you might have one which lies above this, and you assume that it's separated by a gap. This is an assumption, and I will make later on a comment about it, which is not always fulfilled. Yeah, but it is, for what we are doing, a crucial assumption. And maybe at some point in our Delta project, we come into cases where this is not fulfilled anymore. And actually, topological effects appear exactly then. But I'll come to this in a minute or in a couple of minutes. Okay, so, and so the idea is also of the Born-Oppenheimer, the nuclei, they are assumed that they are close to a classical equilibrium position X upper knot. Yeah, so there might be vibrations or something, but it's assumed they are essentially close to. Okay, so now I just mentioned some technicalities about the Born-Oppenheimer, but will not dwell on this in much detail. So these eigenvalues can be expanded in powers of this kappa, which is very small, the electron mass divided by the sum of the nuclei mass. And Born-Oppenheimer showed that in first and third order, the contributions vanish and only zero quadratic, quartic, and higher orders remain. And they could, I'm not 100% sure, I think they, yeah, they computed the zero, the quadratic, and the quartic order, and the higher ones were then correction terms, which they didn't compute. But this was extremely difficult and very powerful. Okay, some history. All of this, Born-Oppenheimer was a fantastic work, but for a long time it wasn't clear what mathematically was behind it. So the first thing you need is that the molecular Hamiltonian is self-adjoint in the sense of mathematicians, which was proved by Cato in the 1950s. And actually, a colleague of mine at the University of Colorado, a chemist, I was very happy. I mean, it seems that, I mean, he had a book of Cato's perturbation theory of linear operators in his office, and it seems that chemists are very interested in Cato's work, even though, I mean, Cato was very pure mathematics. Okay, and this full expansion by von Oppenheim that's mathematically makes sense was proved by Seiler and a few others in the 70s and in the 90s. Okay, so let me now come to an example. It's not one of a particular molecule or something, but that's how a potential energy surface could look like. Yeah. So what do you see? Well, it has local maxima like this A here. It has local minima like the B here. And it has saddle points like at the 1 and 2. And it's just, if you have a more complicated molecule, then it might be in dimensions going into the hundreds and maybe even thousands. And you have hundreds and maybe even thousands of local maxima and minima. Yeah, so this is an idealization, but in principle, that's the picture how one thinks a potential energy surface looks like. Okay, there are already in this picture a few idealizations. So maybe some of the grad students have an idea what are these idealizations? So I usually in my lectures ask always questions for the students. So I'm not sure whether that's a good idea in a webinar, but I just give it a try.
Smooth.
Yes, perfect. I mean, it works even better than in class. Thank you for the quick and correct answer. This is a smooth surface. Why is that the case? And this is not at all clear, at least not to me. And I actually do not even know of a proof why it should be smooth. Yeah. So this is maybe when, for our Delta project, I think, I mean, maybe not as the main thing, but on the side, I think we should also look into some questions on the mathematical side and maybe study to make some progress there. So why is it smooth? That would be an interesting thing to study. In addition to this, it's also, I mean, when you look at this, it's a so-called Morse function. So the critical points are all non-degenerate, and Henry will explain in this talk, I think, in 2 weeks, the details of what that means. But that's even more restrictive. So you cannot have long constants and then it goes up and down again, yeah, for example. And so, so you have the non-degeneracy of the Hessian at each point. So why is that the case? Also not clear. Okay, but there's another question. I mean, we want to look into topology and, well, the features we have discussed right now are analytic geometric, yeah? So local maxima and minima saddle points. So these are typical question of analysis and geometry. But where's the topology? Another question for the students. Where's topology here? Just make a guess.
The level sets.
Pardon?
The level sets.
The level sets. Okay, that is actually that's where I'm heading for but it will be the second step. Yeah, so you are correct. But at first sight, if you just look at this energy landscape, there is no topological non-triviality. It's actually, I mean, what does topology mean? The topology of this guy is in principle trivial. So you don't see it immediately. And one needs to check, and that Enrique was, I think, Enrique, did you answer this, say this? Or who was it?
Yeah.
Anyway, yeah.
So, Marcus, just going back to the previous point and perhaps connecting to this one as well. The energy landscape is smooth if you're working in a space where you don't allow the nuclei to overlap, right? Because you do have singularities when two nuclei are coincident.
Yeah, okay.
So
This is
if we and that might not be just a pedantic point, because if you're thinking about the raw landscape in terms of Cartesian coordinates, you haven't yet removed those kind of singularities from this.
yes.
From the space.
Yeah, but
That is,
those aren't going to occur under like the normal evolution of the system, right? I mean, you could, if we're not studying nuclear fusion, right? So I think, but the other point I would say too
No,
is that,
I agree with that, Aurora. But the point is, in the if we are trying to represent the topology in that space, those points exist whether we sample them or
sure,
not.
that is correct. I agree with that. The other key point here
yes.
is that if this is along a single electronic state, right, then you can have crossings of electronic states, and you also get singularities at crossings of electronic states.
Yeah. Okay.
But we're not going to be getting any of those because we're going to be doing the kind of dynamics we're doing, even in AIMD, are going to either be along they're going to be along an approximate ground electronic state surface.
Yeah. Now, this is a very, thank you very much, Shankar, and Aurora too, for your comments. And this is something I have to look into. I mean, I fully agree. The main difficulty is when you have overlapping nuclei coordinates, and assuming you take this, I will mention this later on, the fat diagonal out. Nevertheless, I mean, mathematically, really having a rigorous proof that it depends smoothly on the coordinates. I have to think about this, but maybe we can discuss this at some point later. But I think you're right. Okay, so the topology at first sight looks trivial. And now the main question is, how does topology come in here? Okay, so, and the problem, it has to, so, I mean, Shankar gave an important point already. The topology of the domain of the nuclei coordinates is topologically trivial. Yeah, so in principle, the potential energy surface is so too. So how does it come in? Okay, the first thing is via cutoff energies. This is kind of similar, like Enrique said, with this level sets. Yeah, so the level sets are, you cut certain levels of the energy, and then you get non-trivial intersections and of a non-trivial topology. The other one is you just look at all at this surface below a certain cutoff energy, and this surface that has a different topology. That is, both aspects are very closely related to Morse theory. And actually, these are the fundamental ideas of Morse theory, even though Morse theory was not invented with a view towards energy landscapes, but it's exactly that main aspect. And Henry, I think you will talk much more about this in 2 weeks, so I will essentially leave it. I mean, I will later on give a cutoff energy example, but other than that, I'll leave it at this. Okay. So here, okay, we have again the topology becomes apparent via Morse theory. So the second one is the failure of the Born-Oppenheimer assumptions. They can result in topological effects. So, for example, let me explain, and let me now give this a try. I hope it works. Well, no, it will not work here, but I'll try this later on. So what the point is, if you look at the lowest energy eigenstate and then at the second one, I mentioned that it's assumed to be gapped. But if you do not have a gap and these two surfaces touch, then they can touch in a conical intersection. So it looks like a lower cone, like a cone when these two touch. And that immediately changes the topology, and it actually it's measurable. For example, the photoelectric effect is a topological effect, a quantum mechanical topological effect of the energy landscapes, and of the first one and the second one touching. And the last one is exactly what Shankar mentioned. If you have to remove the fat diagonal, that means all the subspace where two two nuclei are at the same position. That you have to take those out. And this Rn taking out, where you take out this fat diagonal, that's a highly topologically non-trivial space. Yeah, I am not sure though how much this will affect our research, but it's mathematically, it's there, and it's relatively well. Yeah, well, it's there are some difficult studies on this, but okay. Questions so far? I'm actually much faster than I wanted to be, but.
Marcus, I just have a question. We're getting some audio feedback. I don't know if you can turn down your, if it's maybe your own volume, if you turn that down, if that will help, or maybe if you stay a little further away from the microphone. I don't know.
Maybe is it better now?
I think it
Yes.
might be.
Yeah. If you are a little away from the microphone, I think it is better.
Okay, so I'll speak like this.
So the only other comment that I'd make, Marcus, is that the challenge of solving the Schrodinger equation is really not fixed by the Born-Oppenheimer approximation. It's really in the design of the effective Hamiltonian that gets you around the issues associated with the integrals of the 1 over R12 term.
Yes.
And so the Born-Oppenheimer approximation certainly is really, really effective, and it does reduce the the dimensionality of of what you have to solve in the context of the Schrodinger equation by limiting it to just the electronic surface. But I'm glad that you're talking about kind of conical intersections and things like this. I'm not sure, it would be very interesting as a stretch goal. We can certainly construct conical intersection-based energy landscapes. But and there's some very well-known ones that we could pursue if we were interested, maybe as a preliminary work, maybe for if we can demonstrate that some of the methods we're using are effective for ground state surfaces. Understanding coupling would be a very interesting thing, I think, and that would allow us to start talking about excited state chemistry and photochemistry and all sorts of things like that.
Yeah, I mean, thank you, Aurora, for mentioning this. I have mentioned this in particular because it seems there is, since a couple of years, a lot of literature evolving around conical intersections. I mean, in chemistry for a long time, but meanwhile also in mathematics. And there are these important effects like Barry phase, intermetric phase, and so on. So it's a source of great topological effects. Let me put it that way. And we will see over time how much we can go into this, either theoretically or experimentally, or a mix of both, or numerically. Okay, so now let me just, this is the example Shankar created for our proposal, and it's, maybe I'm the wrong person to explain this, but Shankar, feel free to jump in and add. So this is an electrophilic attack reaction. Why I mention this is because here you see the effect of the energy cutoff. Let's first look at part A. What is this? So in alkene, it undergoes an electrophilic attack by an hydrogen ion, and then it goes into the state 2, and now the single bond here is free to rotate. Yeah, and then in 3, the hydrogen ion can be removed, and then what can happen, it need not, but what can happen is that you have a switch from a cis isomer to a trans isomer. And whether this is possible or not is very much dependent on the energy, so to speak, you put into the system. Yeah. So now let's look at B. So you mod out rotational and translational symmetries of all of this, and here on the right, that is a kind of a reduced energy landscape. And you see, if you cut off, let's see, very low here, what would you get topologically? You would get 2 connected components corresponding to 1 and 3. If you go higher at some point, these 2 connected components merge into 1, and then you get this circular shape topology, which is different to the one had before. Yeah, by just changing the energy and cutoff, you get in topologically different regimes, and that gives you information about the chemistry. Yeah, and this circular circular topology, it happens exactly at when you can have here this rotation and switch from cis to trans. Okay. Now questions so far, because now I want to well, actually it's exactly half time, so now I want to come to the so far looking disconnected component, but the goal is to connect this, namely topology. But questions so far? Shankar, do you want to add something, or or
I have a question.
Yeah.
Did you say that there was a quotient involved in making one of the topologies, I guess? Was there a quotient somewhere?
A quotient?
You said lotting out, so I wasn't sure if that meant.
Let me see. Where did I mean?
The rotational symmetries, you said?
Oh yeah, now I know. Okay, so this is what you do is when you look at this R3N, and you always can take out translational symmetry. Yeah, so meaning you can take out 3 coordinates and just work in the center of mass system. Then you have rotational invariance that you can take out another 3, so the 6 dimensions. And so that's what is meant here by reduction. So you just reduce by all possible symmetries. Yeah, and you always can reduce the global translation invariance and rotational invariance, but that does not get you much more above 6. Yeah, so this is if you have a big molecule with, let's see, 10 nuclei, and well, the electron can be much more. So this reduction will not give much, but in this case, it already gave some significant reduction of degrees of freedom. Does that answer the question?
Yeah. Thanks.
Okay, so now let's come to topology. So what is a topologist? I mean, you all have heard this joke that a topologist is a person who cannot distinguish between a donut and a coffee mug. And I mean, besides what truth is behind of this? So a topologist is not so interested in the distance between 2 points on the surface, whether it's the torus or the coffee mug, but under aspects which are deformation invariant, or how topologists would call it, homotopy invariant. Yeah, and one important information about the topological space which has this property is the so-called homology. I mean, I will later explain the so-called simplicial homology. So what does one do? So if you have a surface, whether it's 2-dimensional or higher dimensional, like an energy surface, or a cutoff one, a level set, or whatever kind of space, you want to associate to it algebraic entities which do not change if you continuously deform the underlying space. Yeah, that's this deformation invariance. And now today what I want to do, I want to give it a little introduction to to the main idea of homology. Actually, the one how it historically I think came up first, yeah, namely the simplicial homology. So we need to understand what are so-called simplicial complexes. So let's start very simple. What's a geometric K-simplex? So you have K plus 1 points in Rn. N can be very high, and assume they are finally independent, meaning that you take A1 minus A0 up to AK minus A0, and they are linearly independent. Okay, and you take the convex Haloff those k plus 1 points, what you get out is a so-called geometric k-simplex. Yeah, I will later give you pictures, so, but let's for now have this abstractly. Okay, and what denotes this by this k plus 1 tuple A0 in square brackets. Okay, then there's the standard k-simplex. That's just where it's the delta k in rk plus 1. It consists of all k plus 1 tuples t0 up to tk, such that each component is larger or equal than 0, and the sum of them is 1. Okay, and this is either denoted delta k or in the notation above here, E0 up to ek. And what is EI? Well, that's just the standard basis of RK plus 1. Yeah, so it has 1 at the I spot and 0 else. Okay, so we have now know what the simplex is, and because you have this, these A naughts, they are called the vertices of the simplex, and they are coming in order. And usually we assume our simplices to be ordered just by the order of its vertices. Okay, let's look at the picture. What's the zero simplex? That's just a point in some line. Yeah, you just take an arbitrary A, and A, that's just a point. If you have one, I look at a one simplex, you need 2 points, A and B. They may not coincide. Yeah, that's this finally independent says A and B are different. And what's the one simplex generated by A and B? That's just the line connecting them. Yeah, that's here the one simplex. 2 simplex, okay. You have 3 points, A, B, and C. The affine independence just means that these 3 points are not all on the same line. Yeah. So and then you take the convex hull, so which means it's just everything, yeah, in this triangle. Yeah, that's what this convex hull stuff means. Okay, you go on. So here you get this 3 simplex or tetrahedron. So you take 4 points again. Affine independence means they are not all in one plane. Yeah, and you take the convex hull and you get this tetrahedron out. Okay, but they can be very weird. I mean, this is a rather symmetric triangle, but it can be really strange looking. It's still a 2 simplex. Okay. So now, what is a so-called simplicial complex? So what one does in a simplicial complex, you build geometric figures out of simplices by gluing them together at their faces. So what is a face of a simplex? So you have here a k simplex given by a 0 and a k. You choose any L, which is less or equal to k, and then L plus 1 points, AI naught, AI1 up to AIL. And these points then form again a simplex. Yeah, it's an L simplex now, and it's called a face of the original simplex here. So let's go back to this picture here. So if you go from D to C, that's the face of this 2 simplex, yeah, or B, C, D here is the face of this 3 simplex there. Okay. So, and now, what is the geometric simplicial complex? So this is the collection, and it's assumed to be finite, of some simplices in some fixed Rn. The simplices can have different dimension. Yeah, that's important. So, and this collection has the following property. If 2 faces, every face of a simplex is again in this collection. Okay. And the second is, if you have 2 simplices in this K, in this collection, and you look at the intersection, then the intersection must be a face of both of these simplices. Yeah. Okay. This is a relatively restrictive condition, but it enables that one can do what we want to do, namely build up a homology theory. Okay, so here is an example. It's actually, as you see from Wikipedia, so nothing very complicated. Here you have a tetrahedron, you have a couple of triangles, and then a couple of, here's this, just a point lying around which is not connected. But the important thing is this triangle and this triangle, they overlap in this face, in this common face, which is a one simplex, yeah? But this triangle, they intersect only in one point, which is it's a vertex of each of them, yeah? So you would not be allowed to glue here a triangle because here in this line connecting these two vertices, these points in here are not vertices of the simplex here. So one needs to be a bit careful, but I think this picture gets the idea. Here, okay, there is the torus. You all know the torus. That one can you can write down as a simple complex. I mean, I don't think I need to explain much more. It's a build-up out of triangles, yeah? And what you want to do is, if you have a geometric figure, you want to triangulate it. So essentially what you want is you want to build in triangles, vertices, lines, tetrahedra, and high-dimensional simplices, just making this geometric figure into a simplicial complex. And there's a very, very fundamental theorem by Whitney, which tells that there's a smooth manifold. So it can be triangulated. So there is a simplicial complex essentially, which essentially makes this, yeah, approximate is the wrong thing, but for each manifold, you can find a triangulation, meaning a simplicial complex, which is topologically the same, homeomorphic to the original space manifold. Okay, questions so far? All good?
Good here.
Okay. So now, assume to be given a geometric simplicial complex, or these are type. Is the audio still okay, or should I maybe, has it become a bit better?
Can you turn your microphone down a little, the level of your microphone?
Frankly, I don't know exactly how to do this.
So in Zoom, in the left bottom corner, there will be a microphone button. If you click on the options.
It's on Zoom. On the no, where is it? No, I don't.
Oh, it's all right, actually. Or if you just stay a little further away from the screen.
Okay, I'll stay away. Maybe I'll do like this. Okay, so
that's good.
Now
thank
assume,
you.
Okay, thank you. Now assume that we have a geometric simplicial complex. So just the gadget I mentioned before, and you look at k simplices, and give that a name, call it k lower k. And when you have that, what do? You form the so-called k chains of that simplicial complex. What is this? Mathematically, it's the set of formal linear combination of k simplices. Let me give you the formula. So C lower k of k consists of all formal sums here, Ci sigma I, where the sigma I are k simplices, and so the Ci are coefficients in Z. Later on, I mean, you can actually choose any abelian group instead of Z. So often Q is chosen, or R, or a finite field like Z mod 2. Yeah, I'll have written it down here only for the most fundamental abelian group, namely Z. But in principle, you could also have this with coefficients. Then you would have the k chains in K with coefficients in this abelian group. Let's say Q or R. Yeah, and actually one needs it later on. But this concept of formal linear combination is a bit of an abstract one, but it's extremely important. So if you would have coefficients in R or Q, you would say the K simplices would form a basis of the K chains with values in the field Q or R. Okay, so maybe a reminder to your linear algebra course. Here, the typical notation is this one, Z to the power KK in parentheses, which means maps from KK to Z, but only finitely many are allowed to be non-zero. That's what mathematically this formal linear combinations mean. Okay, then you have a so-called boundary operator. It maps from ZK of K to CK minus 1 of K. And because these K simplices form a basis, well, a bit in inverted commas, this word basis here, but they form a basis, you only need to define this boundary operators on the K simplices. And here is the formula. So the boundary of a K simplex is the alternating sum of all of its faces which are K-1 simplices. So how many faces which are K-1 simplices does the simplex sigma have? Exactly K plus 1, namely you take out one vertex. And you run through all of these and sum up in an alternating way. Yeah, that's this formula. So this A roof here just means leave that one vertex out and the rest leave it as it is. And that's, by the way, why this notation is with these square brackets is pretty useful. You immediately see what you get here is a K minus 1 simplex. And well, you just run I with your I from 0 to K and sum it up with a sign in front, and that's your boundary. So what properties does this delta have? Well, the fundamental observation, its square is 0. Yeah. So if you apply partial twice, then 0 comes out. Okay. This is a phenomenon if essentially for every homology or cohomology you need such a differential whose square is 0. Yeah, and in mathematical terms, you want the kernel the image. So you want the image to be contained in the kernel so that you can form homologies. Okay, but let's go further. Okay. Now, in our space of K change of this little complex, we can form the space of K cycles. So these are all K chains. Let me just come back here. So K chains are the elements here of the C lower K. These are the K chains. So these formal linear combinations. Yeah. So a K cycle is such a K chain with the property that if you apply this differential, then you get 0 out. Okay. So there's another space, and that is the space of K boundaries. And that consists of all those C's, all K chains, with the property that they lie in the image, meaning there's the D, which is a K plus 1 chain, such that Z is the part of D. Okay. And now this delta squared is 0. It has a fundamental consequence. Question for the students: what is it? What does this property here, this fundamental observation, entail for DK and BK? Any ideas?
Image subset of kernel.
Yes, exactly. The image is in the kernel. Yeah, the BK sits in the ZK. Yeah, every K boundary is a K cycle, but not vice versa. And what is homology theory? It's measuring the defect of a cycle to be a boundary. Yeah. So by fundamental observation, the BKs, That's a big unfortunate typo. This must be ZK. I will correct this. Yeah, so BK is contained in ZK. So this is not wrong, but it's not what I want. Yeah, okay, what I want, yeah, here it's correct again. You know, sometimes typos happen. So the kth homology of this simplicial complex is the quotient of the cycles, of the k cycle space modulo the space of k boundaries. Yeah. Okay, and this is the important consequence of this fundamental observation: partial squared is 0. So now we have the so-called homology groups, and they are labeled by the integers. Yeah, so you have a 0-dimensional homology, a 1-dimensional, and so on. Okay. So, and now for any such a simplicial complex, you can compute the homology. So it is now at this point, I mean, as I mentioned before by Hassler-Whitney, every manifold, like a sphere, a torus, a coffee mug, I mean, what, a torus, yeah, what else? I mean, Klein bottle and so on. All of these spaces have triangulations, meaning they can be represented by simplicial complexes. Now, what question does arise there? If you have one manifold, one space, but you can represent it by two different simplicial complexes. So what's the question which arises? Again, for the students.
Are those simplicial complexes homeomorphic?
Well, that's yeah, that's actually, that goes into the so-called Hauptvermutung, which was a fundamental mathematical problem of last century. I will make a comment on this in a minute, but this is, let me put it this way, that's the too difficult question. But what's the easier question?
Do they at least have the same homology?
Yes, exactly. And what's your guess?
Yes.
They do, exactly, yeah? So this is the fundamental observation. If you have a space which is nice and smooth, like a manifold, and you have two triangulations by simplicial complex or representations as a simplicial complex of the space, they give the same homology, and yes, they do, yeah? So this is a very fundamental observation. Let me, because we still are in time, let me just make a comment on this historically very important question in mathematics. And not quite 100 years ago, but I think around World War II, one important question was, so you have a space, you have two triangulations. Is there one which is a refinement of both? Yeah, so you can make a triangulation finer, and you say two triangulations are equivalent if you find a common refinement. And the so-called yeah.
Could you, I think you're getting really glitchy. Do you think you could turn off your video and let's see if that helps with the audio quality? Because I'm only catching like every other word.
This is really strange. I'm very.
Oh, you muted yourself. You need to turn off your video, not the audio. It's okay if we can't see you, but it's not okay if we can't hear you.
So is it better now?
Yes, that's amazingly better. Let's give that a shot. Thank you.
Okay, it's strange that this, okay, anyway. So, a long question, but it's all that is wrong in dimensions larger than 3, I think. So that's no point, unfortunately. Okay, let's just go for some examples. So homology groups of spheres. So there are the homology of the is D in the line in K is 0, or K is the dimension of the sphere, and otherwise it's 0. And the torus ring.
I'm really sorry to interrupt you again. your audio just got really weird all of a sudden. Like now it sounds like you're in this big echo kind of chamber thing. I don't know if you, it's very strange. It is. Yeah, poor Zeb. Everyone, the sound is really, really bad. I'm not sure what's going on. But yeah, like it really just totally changed just now too.
I'm a bit, let me just see whether.
That's weird because now you sound fine, but as soon as you start talking about math, it goes all wonky.
Okay. The point is here, I don't see anything where I can change something. Maybe I speak a little with lower voice. Is that better?
Yeah, this sounds fine. So I'm going to keep my fingers crossed.
Okay. Okay, I'll try to be more. Anyway, so if you look at the torus, then the homology groups are in dimension 0 and 2. They are again Z, but in dimension K is 1. The homology of the torus is 2. And if you go 3 and above, it's 0. The last thing I will mention today are the Sorbet numbers. And we'll explain here of these homology groups. So the numbers are the dimensions of these homology groups. Any coefficients in Q are that it's only, this is not a too big issue. So if you go back here, the first, what are the numbers there? So in 0, the number of K is 1, the number would be 2, K is 2, that would be 1, and it will be 0 otherwise. Yeah? So, and how can we interpret those Betty numbers? The number of components. So you have a one, there are more than components. The number of dimensional holes. Yeah. So if you look at the circle, it's a one sphere, so it has Betty number 1 is 1, so it has 1 two-dimensional hole. And in principle, you go on this beach number of 3-dimensional holes, and so on. And these numbers give important information about technology. So in principle, I mean, going way back to, let's see, to the energy surface. So you do here some cutoff and below, and then you look at when you cut off this here, so to speak, what kind of dimensional holes do you get? Yeah, what are the value numbers? This goes more into more detail, and we'll explain much more about it. But that kind of, at this point, I guess I can make the connection. It's relatively thin at this point to the first part of my talk, and that's how the topology comes in. Okay, I guess I leave the remaining 2 minutes for questions. Are there questions? Or maybe 2 minutes?
Well, no, I mean, I think part of it was just because of the audio stuff. So, but I guess in the context of the Betty numbers and creating like this barcode, right?
Yes.
In principle, I'm wondering. So you start off with the structure, you know, construct it as this series of points, you increase your radii and you look at which points the components become connected, and you're monitoring the number of holes and their dimensionality. Is there any way to go backwards? Like, let's say you have an algebraic topological sequence of Betty numbers or something like this.
Yeah.
Is it possible to go backwards and reconstruct the three-dimensional geometry?
No. This is
too much information.
No, it's not. And so meaning there are spaces which have the same homology, but they are not so they are not the same, so to speak. Yeah, so they are. So you cannot if. So it's more the other way around. That if you have two spaces having different Betty numbers, you know they cannot be homotopic or homeomorphic. But you cannot conclude the other way around. If two spaces having the same Betty numbers, you cannot conclude that they are homeomorphic or homotopic. So this is actually, and this would be amazing if one could get that, but that's not that's not
I mean,
possible.
really, this is like an information content issue, right? When
Yes,
you
yes.
you
It's
lose a
not
lot of
economic.
information,
Yes,
right?
yes.
So one could consider, are there groups of topological descriptors like Betty numbers in conjunction with a series of other descriptors perhaps that then would allow you to have more of a one-to-one mapping between the full three-dimensionals or the whatever n-dimensional object that you have, right? And its
Yeah.
actual geometry, right?
I mean, this touches an extremely fundamental question in topology, whether there exists kind of exhaustive, I mean, just it's difficult to say, functors, let's say, and so far there doesn't exist something like this. Yeah, so it's always difficult to compute with geometry and topology, or with spaces. Yeah, I mean, what a computer can compute with is with numbers. Yeah, so algebraic entities. So you always have to translate a geometry or topology into some algebra, and then you do your computation. But this will always be a certain approximation. Yeah, it can be relatively fine or fine for the content you want to know, but it's not exhaustive. So a one-to-one mapping, it doesn't exist. Yeah. I mean, more finer information would be the homotopy groups. Yeah, but they are much more difficult to be computed.
Well, it may be that there are some levels, because we are dealing, energy landscapes have, in some sense, there are some rules associated with the shapes that you observe, right? And as a consequence of those rules, we may be able to consider whether they allow more of a direct mapping.
Yeah, I mean, one has to say, though, that with Morse theory, we can, in principle, with cutting and pasting of and using Morse theory, you can, in principle, construct every manifold. But this is not just giving the Betty numbers and you're done. So this is a kind of a surgery approach. And I hope Henry, I think left for another talk or lecture already, but maybe he can make some comments when he gives his talk about Morse theory, how using these cutting and pasting and surgery tools, you can in principle describe theoretically any manifold. Yeah, but it's just by Betty numbers or homologies, it's not going to work. Yeah, it's nevertheless the invariants are nevertheless good and pretty fine. Yeah, it's in particular thinking at the how complicated these structures are. Yeah.
Sure.
Is this non-uniqueness issue also present with the barcodes? Or because you're also keeping track of the radii, so does that give you more of a uniqueness result than just knowing the Betty numbers?
I know what you mean. No, that will not. No.
Well, it does give you some level of spatial relationship between whatever the features
It gives
are, right?
some,
But it only does that in a radial way. It doesn't do it in a, it only does it in one dimension.
Yeah.
So in the case of like a reduced energy landscape, depending upon the level of reduction, I would imagine that the barcode might be somewhat unique, right? And that would be kind of interesting to understand how the uniqueness changes as a function of the dimensionality of the landscape that you're talking about, perhaps.
Yeah. Okay, further questions or comments?
I guess I have one question.
Sure.
So even, I guess I guess we were talking about how the smoothness, it might be smooth for the cases that we're interested in, but is it still, maybe it's just because I don't really understand the dimension reduction techniques, but does it matter if it's not smooth after reducing the dimension, or?
Well, reduction usually destroys smoothness, and it depends on the kind of reduction you choose. I mean, there are geometric reduction methods which essentially reduce by symmetry, and you always use by translational symmetry. All that and the signal, I think, will rotational symmetry, you reduce that, you can already get some that's but there's whatnot, and this it can, I mean, it's a difficult undertaking, and my understanding is that the theory is lacking behind there a bit. Yeah, so people use it, but it's not that as far as I know, that hasn't been studied much. So maybe at some point, a couple of people here at Delta get together and look into these things, and maybe write an overview article on various reduction methods and the favors and what do they destroy smoothness and so on or not. So, for example, this cyclooctane paper, which Henry mentioned a couple of times, I think they used the PCA method of reduction, and then they got a stratified space. So it's not smooth anymore. But in a certain sense, it made it even more interesting. Yeah, I mean, you cannot apply, well, actually, there is a more stereo of stratified spaces. So it's, if you lose smoothness, you have to channelize your theoretical approach to more stereo maybe. So there are ways out, but there is no let's say, easygoing way. And there's definitely a lot of theory involved, which is not solved yet, to my knowledge at least. Yeah.
Well, I mean, I would also point out that I think chemists, I think if you started seeing non-smooth surfaces, we're going to need to be able to, on some level, right, we need to maintain this balance between mathematically interesting and challenging, but still intuitive or meaningful from a chemist's perspective, right? And
Yes.
so it doesn't mean that if we can traverse those boundaries, I think that's good. But in the end, we do have to be able to describe a surface to a chemist in a way that is meaningful to them. And that is going to be hard, I think, if we kind of get those kinds of surfaces.
That's true. Yeah. Even though, frankly, you don't know. I mean, it could be like in the cyclooctane paper. In the end, it was, I think, a Klein bottle glued to a sphere or something, which actually looked quite nice. Yeah. So it is a problem, and I fully agree. One needs to do it in a way that, at the end, chemists, it's understandable for chemists, geometers, topologists alike.
Mm-hmm.
Yeah, but there is something to do. Let's put it that way.
Yeah.
There is no immediate and ad hoc and clear answer.
Awesome. Okay, well, we should probably stop. Thank you so much, Marcus. This was really good. I think it was nice to kind of explain things to both chemists and mathematicians, so I really appreciate it.
Thank you. I appreciate it too.
Thank you. Okay, we'll have another webinar in a couple weeks with Henry and Enrique. I think are going to be working on that together.
Sounds good. Thank you.
Great. Thanks, guys. Bye.
Bye.